I will start recording to the cloud, and what we'll do today will be to discuss how to compare the two methods for shortest path. So we did an implementation using depth first search and an implementation using breadth first search. And what we like to see is how they compare, mostly initially based on the execution time. So sure, you can do a theoretical execution time, and that will give you the same result. But what I would like to do in this lecture is to do an empirical execution time study, looking how fast a medium graph, for instance, the medium graph is computed. And as you remember, the medium graph had only one connected component. So basically, when you compute the shortest path, you will compute the shortest path with all the vertices. So it will be a pretty big computation. So because of that, it's I assume it will be an interesting and relevant result. Let's see what we'll get. I haven't done this before, so doing it now, we'll see if we'll have significant result. Now, so what we want to do is to create a kind of analysis, so a shortest path analysis that will be somehow similar with shorter. Oh, I forgot to share my screen. So let me share my Eclipse with you. So what we want to do is to compute the shorter path analysis, and basically here we'll compare the two methods that we created, and we'll do one test method that will be static and can be void because it's just a test. And what we'll test will be based on a file name. So we'll receive a file name, and we'll test the graph stored in that file to using the two methods, and we'll print the results for each of the method and other operations. So we want to do a time analysis for this graph. And sure, if we we can start with a tiny just to see that it's working, but tiny, it will not give us a good statistic. So next we'll try the medium. And here I put test graph is a name. So we type broad, tiny, and medium, and we have both of them. As you know, the large one is taking a long time, so we'll not go there if we don't need to. So the beginning, it will be very similar with the beginning from here. The only thing is that right now I don't want to do a lot of printing. I want to get times and then print the times. And basically what we'll have here first will be to create the graph and then to process the graph. And for the sake of example, we'll collect all the time, and we will print all the analysis. So let's remember how we did. the time analysis? Sure. We have a stopwatch that we can use. The stopwatch we created with okay, so let me put here. So let's put like this so it's clear. Now, when we want to start the computation, we can put start watch, which will start the watch. And when we want to see how long it took, we call elapsed time, which will return a long, and this will be time to create graph. So this will be the first time to create the graph that we will store. Now, next thing that we want is to restart the watch and go to the next operation. And when the next operation will be to compute, like we did in testing for this first search, we want to compute the test. We want to compute the shortest path. And now we need to decide if we do it for all the vertices. And doing it for all the vertices will increase the time. So we'll get a more higher time, or we start by trying to do it for one vertex. And this also might be useful because doing it only for one vertex, we don't risk to take too long. So let's try to do it for one vertex, and then if the time will be too short, we will increase this to do it for all the vertices. So let's and again, we don't want to print anything because printing takes a lot of resources. So we don't want to do that for now. So here we'll compute the time for so this will be the time for shorter path using this first search for one node. And we'll do exactly the same for the breadth first search. Now, keep in mind that when I create this method, it's also computing the depth first search, the shortest path using depth first search or using breadth first search. So just by creating the data structure, so let's put here shortest path, depth first search, shortest path, breadth first search. It's calling fully the computation. So after we did this, we extracted all the data. So what we can do now is to print the obtained data. And we can print some useful information. for instance, we'll have the graph and we can put with, let's put here number of vertices and I can put here vertices, actually put a space, and okay, let's put the plus down. So this is just a characterization of how big is create the how big is the graph. So we'll know characterization of the graph, and now we'll put the free times that we computed, and it's up to us. We can put them in a table. We can put them in. It's up to us how we want to put. But for now, I'm not. I will just write them. Create graph, and I will let here time to create graph. Then shortest path for 0 using depth first search, and I will put here time for shortest path. And I'll repeat this for the breadth first search. Okay, so now let's see how this works. And before I run, I would like to see your intuition. And I will ask you some questions because anyhow, I want to ask you more questions today. So which one do you think will give us the shortest path? Which method will give us the faster, shorter path? Okay, give me what you have. Okay, so the common sense intuition will be that breadth first search. In depth first search, we compute, we go very deep. So we first compute very long paths. And then when we come back, we keep shorter and shorter paths as we find out better paths to go in a place. So basically the depth first search is doing some additional operations. So let's see if this is confirmed or not by running our code. So let's look. First graph, 13 vertices, 13 edges, shorter path, both of them take us 0 milliseconds, so very fast. And no, sorry. First, depth first search takes 1 millisecond, breadth first search takes 3 milliseconds. So apparently it seems that breadth is slower. Now, if we go to a much larger, the median graph has 250 vertices and 12,000, 1,000 edges. First of all, the create graph is shorter, which doesn't make sense. So it seems like it's an anomaly here of execution. But the DFS now, it's much longer than the breadth first. And that's what you will expect in a real graph. So let's try again. Yeah, so it seems like we will get various values, and each time when we run, we get different values. So what we did when we observe such a behavior, what we did to reduce such a behavior. This is the next question. Okay, give me what you have. Yeah, so I got several, but not to the questions what I asked. I got some other answers. One of the answer was related to the extra time in DFS that is caused by the recursive calls, which is true. The recursive calls are consuming more time, and but it's not only the recursive calls, it's also the algorithm. So both of them will influence the execution time. And so the recursive calls are one issue. Now the other issue is the algorithm for DFS. This will slow down the DFS. And again, why DFS it's taking longer? Because it's going deeper first instead and consume time to go deeper and then backtrack and try better solutions as it found some. So this going deep and then coming back takes some time to execute. Now, my idea was not related to what it's making one of the algorithm faster or other, was just how we analyze the data. And if you remember, if we observe that running the program several times, it will give me different results. What we did was to create a time analysis method that will take some values, will add some values, and will compute their statistics to get the correct value. And that's basically what we'll do here as well. We'll use a time analysis. And how we test, we just create a time analysis instead of stopwatch. The time analysis is creating, we will use the stopwatch, and we'll add the value, the time computed by repeating the execution several times. So each time when we repeat the execution, we add a new value. And now how many trials we'll have generally was variable that we receive as parameters, the number of executions. So that was how we did this, and we did it many times. So I will add here a variable number of executions. So I will keep it in the same so what we'll have will be to have a for int trial equals 0, trial less than number of executions, trial plus plus, and what we'll do will be to repeat this for each trial, and now we'll have a time analysis for each type of so we'll have time analysis to create graph, and let me take this, which will be a new time and sure we can put the file name as a name, but better will be just to put create and so on. And then we'll create 2 more time analysis for each of the operations. So the next one will be for shorter paths. Next one will be for shorter paths PFS. And here we can put DFS, and here we can put PFS as names. So we created now the time analysis, and the next thing to do will be to use these as new data points for each trial. So here we add the time to create graph. Here we'll add to TA for so we just add a new data point in the time analysis, and now the advantage is repeating this several times. It will create a better approximation of the real time needed to do that operation. So okay, what I don't have the graph. So we like to keep a copy of the graph. We know that it's the same graph. So what I will do here, I will put something like this. So the graph variable will stay the same. So I can extract this information. And now, we have all this information related to the time analysis, and Let's see which one we'll use for printing. We can put just a mean time for now. So let's put here okay. Okay, so we put the mean time and now we take the mean time of the last one. So what we did was just to replace trial value with the mean time. Now, how many times I repeat this? Let's put here 31 times. This will give us a pretty good yeah, it doesn't realize that it is initialized. Let me put null. Okay, it worked. Yeah, that's true. We don't use these values. I will put here, and I will put here also unused. We might use them later. So now let's run and see which will be the result. So for the small graph, to create the graph for the 5 milliseconds and the shorter path, as you can see, it's pretty small in average. Now, for the medium graph, we got 3 and 0. So again, the breadth first, it's clearly much faster for normal graph, like here, a median graph. Now, let's try also. I don't know how long it will take, but we may try to see if the large graph, if we can get the large graph. The large graph is very large and might not work, not even in the silent mode like we have here. It still might not work. Yeah, it will stay a little. Oops, we got an error, which is Stack Overflow. Yeah, it doesn't work because a recursive method, it's we need to create, to put a huge stack for the defrosters to work. It's so inefficient is that it will not work. So we are not able to check for the recursive method. But the times for the median graph are much better actually. And now let's think if we want to, because here I just computed the time for starting from vertex 0, and we might want to compute the shortest path starting for any vertex. So this will increase again how we count the execution time. And if we look that we have 250 vertices and 3 milliseconds, or yeah, I think it's in milliseconds. Let me see. In milliseconds. So if we if we are computing for all the edges, we'll get a better result. We'll get a much bigger result, so we'll be able to recognize the value. So let's take a source index that will start from 0, and it will go to the last vertex. And what we want to do will be just to compute the shortest path. So for that particular vertex. So still the time will be very short, but it will be a little bit longer than before. So actually this one will need to come here. So I think now we are done. So let's try to see now when we execute if we get a better time approximation. And let me take, yes, I took out the third test, which it's not easily supported. So you see, the small graph worked pretty fast, but now for the larger graph, it will no longer work so fast because now it's doing the computation for all. So instead of 0 for all vertices. And this is a better approximation because trying to start from various vertices, actually I have different configurations of the graph. So I test with in more situations the algorithm. So it's much much accurate if we do that. Okay, so now let's run it again. And the first graph, as you see, it's still very fast. The second, but it's very small. So the results being under 1 millisecond, and we measure everything in milliseconds, we can ignore that, you know, we need to round the results to be accurate. So the fact that we get various values under 1 millisecond, it's not is not relevant. But for the second graph, now we can see a clear difference between around 373 milliseconds and 6 milliseconds. So it's like 50 times faster the breadth first search than the depth first search method, which is significant. And again, this is not a huge graph. As the graph will increase, as the number of vertices and edges will increase, we'll have even more the size will be even more relevant. Now, let's so that's basically the last task that I will ask you to do. it's to do this comparison. Sure, you'll get other values. But what I would like us to do also is to think, okay, how we can get if we want to point some intermediate values. So now we have a graph with 250 vertices, but how we can get a subgraph of it that has fewer vertices. So that will be, we'll have the same graph, but we want to extract a subgraph and do the computation of a subgraph just to see, to try to create a graph of the initial, to try to create a graph based on the number of vertices and proportional edges, how the time will evolve. Because if we create a few points and create this graph, we'll be able to see how each method it's increasing, if it's increasing linearly or if it's increasing exponentially as an execution time. Yeah, one idea will be to create a random graph. It's a very good observation. So, but to create a good random graph, maybe not so easy. However, it will be a useful method. So let's think how we'll be able to create a random graph. What we'll need to generate for a random graph, and what's the main what we can say, it's okay, I will create a random graph and I will try to create a uniform random graph. What means uniform? So I will try to add uniform edges, not to have like one vertex, to have many edges, others to have very few edges, to distribute the edges uniform, randomly but uniform in the graph. So so what we need to provide to a random method in order to generate a graph? What we need to provide? So we'll need to have very good observation. We'll need to provide both the number of vertices and the number of edges. And if we provide that, we'll be able to create various type of graphs. We can create sparse graph, we can create dense graphs. So just by playing with the number of vertices and edges, we'll be able to test how our method works for various type of graphs. That's very important. Now, let's try to do that. Let's try to create a method that generates a graph, a random graph. And we can add this method so let me close all these editors. We can go in our undirected graph adjacent list data structure, and we can create in it a method that will create a random graph. And these will need to be static method because I don't have yet the graph. This method will need to create the graph. So that's why I'll need to make it a static method. And sure, it will return an undirected graph using a JSON list as a result and create random graph. And what I need to provide will be like the number of vertices and the number of edges. So that's what I will need to provide in the method. And sure, I assume that's possible. So I may test to be sure that it's possible. So for instance, if the number of edges is greater, but yeah, so we need to decide if I allow parallel and self edges and loops, self loop. And let's say we don't. So let's say we want to generate random edges that don't allow parallel and self loops. So basically then the number of edges, the maximum number of edges needs to be less than the following formula: number of vertices -1 times number of vertices over 2. So this will be the maximum number of edges that I can create. And if this is greater, I will just make it this number. So I will reduce it to this number. Now, the main risk here is that generally I don't want to go so dense, because if I use a easy random algorithm, it will be hard to generate dense graph. And the reality is that we rarely work with very dense graphs. Now, let's so this will just guarantee that this is possible. So what we want to do, first we'll create a graph, and to do so, we'll use the number of vertices that we receive. And I will return the graph here. And then I want to create all the edges. So I will start with edge index 0, edge index is less than number of edges, edge index plus plus, and I create this number of edges. And the easiest way to do it will be to get two vertex index and then to create that edge. But that edge may not be valid. May not be valid because it's a self loop, or because I already had that edge created. So what I'll do in that case? So in that case, I need to repeat until I find a good edge. So let's put here a Boolean created, it's false. And we'll have while not created. We repeat this cycle in which we pick two vertices. And let's put vertex 1 will be int of mass random times number of vertices. Vertex 2 will be int the same thing. So basically we pick randomly two vertices, And if vertex 1 is different of vertex 2, is not a self loop, and I don't have in my graph has let me check if I have, maybe I don't have in the, okay, I don't have this because we didn't need it. I will modify here the API to also add a method that will test if I have an edge, which is a very useful method, and I don't want to simulate it because it will take much long to simulate it. So and we'll return a boolean. So let me check this, modify here. So I will return a boolean if I have an edge or not. So I modify the API for undirected graphs, and now I need to create an implementation to check that, and basically we'll just go through. Actually, this is not here. We need to put it up. Number of adjacent agencies here. So what we want to do is to go through all adjacent edges. So, or for instance, vertex 1, adjacent index, adjacent edge equals 0, adjacent edge is less than vertices degree. So I go through the adjacencies for vertex 1. Of vertex 1 index, and I check if they are equal with vertex 2 index. So which is this will be the list, adjacency list of vertex 1 index and AE. And if I find that vertex 2 is in the adjacency list of vertex 1, I return true. If I didn't find it, I will return false. So this will just tell me if I already have an edge between two vertices. So let's go back to our method. So here I'll need to see if the graph has an edge between V1 and does not have an edge between V1 and V2. So V1 needs to be different of V2, no self-loop, and I must not have a parallel edge, so the graph does not have yet an edge. So what I get in that case means that V1 and V2 are good for a new edge. So I will add to the graph an edge between V1 and V2, and also I will say, okay, I created becomes true because I created now this edge. And I repeat this for the number of edges I want to create. Now, it's important to say that if number of edges is very big, so this works well for graphs that don't have a lot of edges per vertex. If the number of edges is high, then I will be in trouble because I will repeat this very many times until I find two good edges, two good vertices for a new edge, because I will just repeat to pick already defined edges or self loops. I will often pick already defined edges. So that's why this method, this random method, doesn't work always. What we can do, we can modify this, and if here to have a kind of else, and if the vertex already exists, instead of generating random another one, just to try to find starting with this one. It's an incremental kind of method that will just increase B1 and B2 until I find a good fit. So we can do that, and that will work faster, but still will take time. But for now, I think this will be good for the type of test we want to do. So let's go back and try to see how we can create another test. And again, we'll need to repeat our test and create a kind of table. Yeah, we get an error if the edge cannot be created, but our representation works with self loops and parallel. So our representation allows self loops, and our representation allow parallel edges. So we'll need to create, so if we want to check the add method to check, we'll need to specify when we create a graph if allows self loops, if allows parallel edges, and then based on the configuration of the graph, the add will need to check those informations. Right now, we haven't done that. We just allowed any kind of graph. But yes, if we will decide to do a more thoughtful implementation, that will need to be added. Very good observation. Now, we created the method, so let's try to test it. And again, what I would like to do is to modify the analysis. So I will leave this test that we did, and I will create now a new method that, so this one I will leave them, but I want to create also a random test that, that will do, so let's create here a public static void random test. And basically I will take here mean vertices, and I will take, let's say, I can take max vertices, and I will take int increment. And also what I need to take, I will not take the I will take a single measure that will be the number of average number of edges per vertex. So I will put edges per vertex. That will be also an int in our case. Can be a double, doesn't matter. It's just to give us how many edges we create for one vertex. And keep in mind that this will anyhow need to be divided by 2, because if we have 5 per vertex, then basically in total we'll have 5n over 2, because for an edge we'll couple 2 vertices, so we need to divide by 2. Okay, and for this, what we'll do will be to call test for the, so we need to create a graph. We need to call a test that will create a graph with a given value. So let's put here random. I'll put first here random analysis and the random test. So I will need to create now a test, random test that will receive number of vertices, number of edges, and will repeat the test above. Both are ints for these numbers. So basically will be similar with here for okay, for these numbers. And okay, so let me take everything. The only difference is that number of executions. Yes, I need to put also number of executions. Which is a kind of precision thing. And let's put this number of executions also here. Okay, so what we'll do at this point after we, I will not print the header, but what we want to do will be for number of vertices, starting with mean vertices, number of vertices less or equal with max, vertices, number of vertices plus equal increment. So we basically take all the values between min and max with a given increment. We'll call the test, the random test, with the corresponding value, with the number of vertices with a number of edges that will compute a number of execution. Now to compute the number of edges, as I said, we'll multiply number of vertices with edges per vertex and divide it by 2. And this will give us a desired number of edges. Now, keep in mind that each test will be randomly generated. So that will give us a nice test. So how we'll call this random analysis will be, let's say we'll start, I don't want to start too low because you see, you cannot see much if you have few vertices. So let's say we'll start with maybe 50 vertices. We want to go maybe to 250. Let me think how we can go. 250, maybe 300 or 500, and let's go 50 by 50 increment, and then we'll put edges per. Here we need to decide. Here we had like 5. So we can keep the same density like in our case, because we started with this, so it will be around 5, it's the density. So each no, 10, here it's 10 density, not 5, because we divide by 2 and we get 5. So so each vertex will have like 10 edges. And the number of execution, let's keep 31, just to get reasonable statistical results. And so we did this. Now let's modify our random test that we copy paste from the previous one. And here, instead of creating a file, we no longer have a file. We'll just create the graph using the create random graph, number of vertices we get, number of edges we get, and we can still compute the time to create, which will be fine. And we computed all these times here. Okay. We like next to also print, but we'll not print on several lines. Let's just print with format. And let's try to put percent. The vertices will be like a 3D. Then we have percent. The edges will go to, let's put here, $10D, no 10, 5D, I think it's enough. And then we'll print the creation time. And these, I don't know right now how big they will go, but let's put I can still print them like around them. So let's put here, I think 5 will be good, 50F percent, 50F percent, 50F. We'll see, if it doesn't look good, and backslash to go to the next line. And sure, we'll need to add all our computations. So we'll start with a number of vertices. We need to add a number of edges. Okay, almost there. And then we like to put the mean times for various operations like before. So to create the graph, I know now it's random, but still, if we have it, let's put it. So then we'll look at the depth first. And keep in mind that here you may have fewer connected components. So there is no guarantee that you'll have only one connected component. You may have several connected components. So depending on how the graph is generated, we don't know how the graph should look like. So this seems like everything. I don't know. Let's see how this will run. Okay, so as you can see, I have 50 vertices, 250. Time to generate is very short. Depth first, 7 milliseconds, 1 milliseconds. Then I have 100, 500, and 0.31. So then when I get 250, it's pretty consistent with the previous result. It was 306, I think. Here it's more because this graph, I generated 30 different graphs and computed for each of them the time. So it's normal to get quite different. But what is remarkable, as you can see, is there is a kind of consistency here. I add 50 at the number of vertices, and basically this double the depth first time, while the breadth first doesn't seem to double, seems to go much smooth. So what kind of growth do you think depth first has in this case? No, the random, I got some questions. The random graph change at each execution. So each execution, if I have 31 execution, each one will go with a different random graph. And that's good because what I want to check is average for this number of vertices, various graphs. So I don't want to check a single graph. I want to check various graphs for this number of vertices. So, and each topology will require a different time to execute. So that's why I know it's another variable, but it's important. But what we want to see is how this evolve. Now we have a problem here because this was not quite double of the previous one, and this one is not quite double of this one. But anyhow, even if it's not double, it's not a linear kind of evolution. So it's clear it's not a linear evolution between them. While here, for instance, you can see it's pretty, I have 6 plus 3 is 9, plus 3 is 12, plus 3 is 15. So in here, sure, the very low numbers you can ignore for breadth first because they are too low to take in consideration. But as long as they start to be more accurate computationally, you see that this seems to be linear for the breadth first. So it seems like a linear evolution. Why here doesn't seem to be linear, which because we kept the same density, and if you look at the mathematical formula, you will see that this checks the mathematical growth for breadth first. While for depth first, we expected something exponential or almost exponential. So again, we somehow prove it's not quite exponential, but or might generate something exponential. What will be interesting now is to take these values, put them in Excel and try to interpolate, try to see which interpolation will work for them. So to try to deduct the function, as we did in a previous assignment. So this will be interesting as a result. Now, again, here it was not 18, it was 19, but it's close to the free. Free, it's just an approximation, can be 3.2, 3.3. So we don't know exactly what it is, but the breadth first seems to be linear. That's something that it's and the depth first seems to be something exponential. That's the idea. I think I have one more. It will take a while, but let's wait for the last one just to have everything completed. Now, this was interesting. So from my perspective, this is the last test that you need to do. And it's interesting because it shows you how much faster, you see at 450, this is 19 milliseconds, and this is like more than 100 more time. So we started with 50 times at 250. Now at 450, we got more than 100 times faster the breath first. So it's clearly much faster. Now here again, it's more than 3. It's 20. I expected 22, but it's clear the time increased more than 3. But it's like 4. Twice it was 4. So maybe more than linear, a little bit more than linear. I don't know, or just how the values were taken. But it's almost linear for breath first. While for depth first, again, this increase was even, it's not double, but it's significant. It's looking like exponential, even if it's not doubling each time. It's less than double, but looks like an exponential growth. Okay, so try to interpolate these results and come up with the functions. That will be part of your homework. You just take an Excel and you take your results, not mine. You just take an Excel, put them in Excel, search for a good interpolation and see what interpolation you get. Questions before you stop? And this will be the last task in your homework, so that's why I wanted to do it before I pause the homework. Okay, if you don't have the questions, I will stop sharing. I will stop recording so I